in Einstein's universe, gravity mass bends the paths, it bends the fabric of space, and that changes the path of light. It takes the shortest possible path, which is now curved. And so when a beam of light passes by a strong gravitational field, it arcs around that field. This is how Einstein's theory was first validated. Arthur Eddington goes to see an eclipse, finds that the positions of the stars behind the...
A solar eclipse, yeah.
Solar eclipse, exactly. To see the night sky behind the sun, and the stars have moved because of the sun's gravitational field. And we see this everywhere now. When we look into the distant universe, we see giant clusters of galaxies, and the galaxies behind them have been stretched out like this funhouse mirror of gravity bending their light, and also multiply image. So you can see the same galaxy at the bottom of the cluster as at the top of the cluster, which you can verify through the spectrum. In the case of quasars, it's particularly cool because the most often scenario is you have a very distant quasar, a more nearby galaxy, and the light from that quasar will take 2 or maybe 4 different paths around that galaxy.
Nice.
And so to us, we only know where the light comes from, so it looks like there are 2 or 4 images of the same quasar.
Was that called the Einstein cross?
The most famous one is called the Einstein cross.
Yeah, because it was a quadruply lensed object.
One of the early ones that was found.
Yeah.
And so what you're saying is there's 4 pictures and they're the same because it's the same source is making the 4 pictures.
One key difference is that they're often at different times because the path lengths are different. So you're seeing the same quasar with offsets of somewhere between hours and weeks. And that's crazy powerful. But
it's almost like you have like a tiny little reset time machine that you're able to observe what's happening.
They're called gravitational lenses because it's gravity kind of acting as this galaxy-sized lens in addition to your telescope. So you see all these new effects of a kind of crappy lens. But if you can model all of it, then you can use the gravitational lens to actually map the inner regions of the quasar, which is still very hard because they're still very tiny and very far away.
Gotcha.
Wait a minute. You're saying the lens gives you deeper access to the quasar than you would otherwise have with just an image of a quasar.
Very much.
So it's a telescope booster.
It's a telescope booster.
Oh, okay.
But there are galaxies we wouldn't otherwise have seen were it not for the fact that they were far away and lensed.